All right, we talked about exponential growth and population with exponential growth, banks and simple interest and compound interest. Today we are going to talk about exponential decay. So we will describe and analyze exponential decay models. You're going to recognize in a formula that models exponential growth or exponential decay the growth factor, because we would have, I don't know, f of n equals a to the b, a times b to the n. This right here is going to be smaller than 1. So when that's decay. When b is greater than 1, it's growth. And we're going to see why that is. So the value of a brand new car drops considerably as soon as the first purchaser completes the purchase and drives it off the lot. Generally speaking, if the buyer of a car tried to sell the car to another dealer or individual just one day after the car was bought, the buyer would not be able to sell it for what he paid for it. That's actually true. Once purchased, the car is now considered used. So let's look through example 1. Malik bought a new car for $15,000. As he drove it off the lot, his best friend Will told him that the car's value just dropped by 15%, and it would continue to depreciate 15% of its current value each year. The car's value is now $12,750. What will its value be after 5 years? So we currently have $12,750. I'm going to see what 15% of that is. $1,912, and then subtract. And I get $10,837.50. So I'm going to take that value, multiply it by 0.15, 16, 25, 63, and then 10,000 minus that answer, I get $9,211.88. All right, I'm going to fill in the rest of this, and we'll come back and talk. There we go. So at the end of 5 years, that sweet little car you're driving around is only worth $4,800. Crazy, huh? So my first question is, what is the ratio, R, between year one, and the start value? So year 1 and the start value. I've got 10,837.50 divided by 12,750. That gives me 0.85. That's my ratio between year 1 and the start value. How about, so there to there is 0.85. How about from there to there? What's that one look like? 9 to 11, 87, divide by 10, 837. I got 0.85. I wonder where that one's going to be, right? We're doing 7,830, 9 to 11, 87. 0.85. I think we have a pattern. Oh goodness, if I could only write. All right. So yeah, our R value is 0.85. So we know what our multiplier is, don't we? So the value of 0.85, what does that have to do with a 15% decrease? 15% decrease, let's see, that is what you have left over after you take off 15%. You're left over with 85% of the car's value. So let's use that information to write an explicit formula for the sequence. It's geometric, so I'm just going to use our usual function notation, equals our beginning value times our multiplier times r, still can't write, raised to the t value. And then use the formula for part B to determine the value of Malik's car 5 years after it's purchased. Round your answer to the nearest cent. So 5 years would be the function evaluated at 5, 12,750, 0.85 raised to the 5 power. Let's go ahead and calculate that. 0.85 raised to the 5th power, $5,657.24. If I look at that table, I'm going back to that table, $5,657.24. Very cool. Use the formula for part B to determine the value after 7 years. 0.85 raised to the 7. I'm going to take a second to point out this value right here is just like 1 minus 0.15. That's 0.85, right? Okay, let's do the 7 years. Got on a little tangent there, sorry. I get $4,087.36. We talked about our function a b to the n. B, when b is greater than 1, we are in growth. When b is less than 1, we are in decay, right? That's what we're learning now. So this just means diminishing over time. Only one S there. Sorry, we could also say something like that right there would mean diminishing over time. Okay, that would be my decay also. Another way to talk about decay, right? This initial value, it's always going to be A. Like that doesn't matter with growth and decay. That initial value it's A. Okay, let's practice a few. Identify the initial value in each formula below. That's A. And state whether the formula models exponential growth or exponential decay and justify your responses. So I'll go through and do the A's first because those are easy, right? Easy peasy. Now, whether it's decay or not. Here we have decay because b is less than 1. Growth, it's a fraction, but it is greater than 1. Growth, because b is greater than 1. Decay, b is less than 1. And last but not least, decay, b is less than 1. Okay, if a person takes a given dosage D of a particular medication, then the formula f of t equals d times 0.8 to the t represents the concentration of the medication in her bloodstream t hours later. If Charlotte takes 200 milligrams of the medication at 6 a.m., how much remains in her bloodstream at 10 a.m.? So 6 a.m., 6, 7, 8, 9, 10 is 1, 2, 3, 4 hours. So we would just do 200 times 0.8 raised to the 4th power. And I have 81.92 milligrams. Don't forget your units. The next question is, how long does it take for the concentration to drop below 1 milligram? I would need the concentration to drop below 1 milligram. This one I'm going to put in my calculator in the table, with that being the variable x, and just look for at what time my answer drops below 1 milligram. Hold on. So there we have it. If you don't know how to do this, I've shown quite a few people, but not everybody has asked, even though I've asked you to. If I put this into my y equals, I don't want to graph it. I mean, I could graph it, but I'd rather look at the table. And I saw that right here it drops below 1, and that's at 24 hours. So my answer is actually 24. Time equals 24 hours. So it takes 24 hours. And you could use a guess and check, but we don't want to do that. So 24 hours to drop below 1 milligram. When you breathe normally, about 12% of the air in your lungs is replaced with each breath. Write an explicit formula for the sequence that models the amount of the original air left in your lungs, given that the initial volume is 500 milliliters. So the original air left in your, so we're losing air. So it's 1 minus 0.12 raised to the time t. So we have our initial value. This is decay, so we're going to subtract raised to the time t. So when you breathe normally, so we're going to evaluate this at 50 breaths. 1 minus 0.12 raised to the 50, and that gives me 500. Equals, I got 0.84 milliliters of the original 500 milliliters of breath. Only 0.84 is left. It changes over that much, which is really cool. And then Ryan bought a new computer for $2,100. The value of the computer decreases 50% each year. When will the value drop below 300? So my equation, I've got my initial investment, I'm decaying to time. When will this drop below 500? So guess what I'm going to do? I'm going to put that into my y equals. One second. Sorry. I cleared it all. Let's try again. Times 0.5 raised to the x. And I'm going to look at my table. And I just want to know when it drops below 500. I think it'll be pretty quick. It looks like year 3, 3 years. And that one is a really easy one to do, guess and check. You could just, that one would be totally easy because you'd only have to guess once or twice before you got there. But my value at 3 years is actually $262.50. And at 2 years, it's $525. So not too hard, right? All right. We keep going. I love these practice problems. We usually don't get this many. Kelly's mom takes a 400 milligram dose of aspirin. Each hour, the amount of aspirin in a person's system decreases by 29%. How much aspirin is left in her system after 6 hours? You guys should be doing these on your own. I hope your homework is as simple, right? 400 times 1 minus 0.29 raised to the 6th. I got, so this would be aspirin concentration, 51.2 milligrams. According to the International Baseball Association, basketball, oh my goodness, starting over. According to the International Basketball Association, a basketball must be inflated to a pressure such that when it's dropped from a height of 1,800 millimeters, it rebounds to a height of 1,300 millimeters. Whew. Maddie decides to test the rebound ability with her new basketball. She assumes the ratio of each rebound height to the previous rebound height remains the same at 1,300 over 1,800. Let f of n be the height of the basketball after n bounces. Complete the chart below to reflect the heights Maddie expects to measure. So we are decreasing each time, right? 1,300 divided by 1,800. That's my R. That is 0.72. So if my function is my initial value times 0.72 to the x, or to the, x, each time, what's it going to be? So my first one should be 1,300. And then it's going to decrease again. 933 raised to the third power, 671, 672, not really rounding well, and then raised to the fourth power, 483. So the chart reflects the heights Maddie expects to measure. Each time it bounces, it should decrease that much. The next says write an explicit formula. Yep, check, got it. You could also say f of n equals 1,813 over 18 to the n. Whatever. Oh, goodness, there's a mistake. That should be an n. Silly me, sorry. Look, my calculations are close. And we got our explicit formula. So plot the points, no problem. The first bounce, well, the zero bounce is 1,800. The first bounce goes down to 1,300. The second bounce, 900 and something-ish. The third bounce, 678. And the fourth bounce, 490. If we look, that's sort of exponential, right? So use the curve to estimate the bounce number at which the rebound height drops below 200 millimeters. I didn't do a very good curve. So below 200, I don't know, around 9 or 10 bounces. Theirs is much prettier, I'm sure. Let's see what my curve looks like. 8 or 9. There's lots of error with this. I always just ask that you guys do your best and try to make it as nice and neat as possible, right? So as a summary, we have an explicit formula that models exponential decay and growth. So A is always your initial value, and B is going to be greater than 1 when it's growth, and less than 1 if it's decay per unit of time. Nice work today.